Okay, who has solved at least one exercise in Lean or did something with Lean last week? Hands up. Uh-huh. Have you? You don't look sus. Have you actually typed any Lean proofs in the last week? Is that a yes? That's a yes. Okay. So I really implore on you that the learning curve is kind of steep. You should be exercising Lean in practice. Okay? This is not about math. This is about knowing how to use the tool. So once you are tasked with your own little project, you are going to suffer if you don't go through the exercises now. You have been warned and it's recorded. If you are experiencing problems, please come to me, okay? But don't just ignore this and think that you're going to do it later. You will do it later, but the effort will be quite a bit bigger, okay? And now I have the time to help. Who knows what I will be doing next spring, okay? So today, we're first going to look at some organizational features of Lean, not all of them at all. And then we are going to, I think maybe is this better? It's probably better. And then we are going to just do some proofs together because I suspect that you people have not been doing your homeworks. Okay, but even if you have, it's kind of fun to watch the lecturer stumble so that you know where you stand, right? I expect you to be better than I am at this, right? When I was a student, we had a Mathematica course. I enjoyed it very much as a student. Okay, so let's do this section, namespaces and implicit arguments. This is quite well documented, so I will introduce you to various kinds of material. I think mathematics in Lean, the one that I told you about last time, is very good at teaching Lean for formalization of mathematics. But there are, of course, other things, like, for instance, the Lean 4 manual also has very useful information. And so there are various sources. So I'll try to tell you what to read because it's kind of overwhelming. I mean, of course, you can just read everything if you want to, but it's kind of a lot. Okay, so one thing I have learned to do, which you might want to do if you play with Lean, is every time you start a project, it downloads 1 gigabyte of stuff, right? Let's see how much precisely. 4 gigabytes, I apologize. So every project that you have is 4 gigabytes on the disk, which is a little bit excessive. So for quick and dirty tests, I just created a project called Lean Scratch, and then I just stick in it whatever comes to my mind because it's kind of silly to have lots of copies of 4 gigabytes of MATLib library. It is a lot smaller if you don't include the math library, of course. The whole business here is that it's, where is this? Lake build lib. No, Lake build one of these packages. Okay, MATLib. How big is this thing? This is the culprit, right? 3.8 gigabytes of MATLib. There are tricks you can make to share between different projects with symbolic links, but it's not designed to work that way. So who knows what will happen when the different copies update themselves. Anyhow, I have a Lean Scratch where we can just put anything we like. And presumably there's some monoidal category stuff. Who knows? There's Steve in there. This is probably Steve Audi. Okay, so let's try one. I don't know how big you want this fonts to be. I don't need this. I can make this a bit smaller, probably. Okay, so the first one is sections. Now we're going to start to see mechanisms that mimic what mathematicians do. Yes. And one of the things that mathematicians do is that they write at the beginning of a section, let x be a real number, or let f be a smooth function. And then for the rest of the section, it's a smooth function. It's actually more likely that they introduce a structure than a single function. They say, let v be a vector space or something like that. And then they work with v. Now, why is that convenient? Well, that's convenient because then in every theorem and proposition or wherever you are, you don't have to keep repeating that V is a vector space. So there is a mechanism like that. So let's see. You can start a section and then you end it also. You can name it, but then you have to also say that you closed it here. Okay. And this is a purely organizational feature that allows you to do the following. Suppose I want to prove theorems about, say, like these are going to be silly theorems, but about a function, say composition. Okay, let's do composition of functions. So first, I'm going to do it without the section mechanism. So without the section mechanism, it would be something like this. Definition. Oh, always set option. I'm really unhappy about this one. Auto implicits to false. Okay, let me explain this first. This is an organizational feature. Okay. This by default is set to true. When it is set to true, I can do this. Def compose. Okay, let me get rid of this. Suppose I want to compose two functions and I say I have a function g from beta to gamma, and I have a function f from alpha to beta. And what is this? Well, this is a function. It takes x to g of f of x. See how it's happy? It's happy. And I can say, what is compose? And you see that here, it produced something more complicated than when I when I asked what is compose. It's actually telling me that there are three universe levels, U1, U2, U3, that beta is a sort in U1, that gamma is a sort in U2, that alpha is a sort in U3. So these are like universes, except even, okay, one day I will explain the difference between sort and type, not today, but think of sort U as a universe at level U. And then I have the stuff that I typed. So it somehow magically introduced all this stuff here, okay? Now, why did it do that? Well, because, see, the thing that I worry about is that I didn't explain what beta was. So it just sort of made it up, right? Also, why am I using Greek letters? I don't know, because they really like to use Greek letters. I could have used this. And then it would be ABC. This I worry about, because as a general principle in software engineering, it's probably a bad idea that you allow introduction of new entities sort of randomly wherever they appear, because it could be a typo, right? So maybe I wanted to say, you know, cow, and then here I made a cow, and then, or let's say here I made an error, okay? So maybe I wanted all four of them to be cow, but now one of them is something else, co. And so this is a typo, but it works because it just happily introduced types cow, 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 cow. Okay. If I say auto implicit's false, then it stops doing this thing. And then it says, I don't know what these are. You have to tell me. And then I have to do it. I highly recommend that you do it, even though this is not what mathematical practice is. In mathematical practice, literally, if I walk to the whiteboard and I just write F:(A) arrow B, nobody will have any doubts that A and B are some sorts of sets. They will know from the context what they're supposed to be. So they're just trying to mimic that, but I think that goes too far. So now it doesn't know. So now I have to explain what they are. Well, okay, so then I will now say, okay, suppose I have two universe levels, U and V, and then suppose A is in Now I'll write type U. A is in type. Oh, I need 3 of them, right? And then I go A is in type U, B is in type V, C is in type W, like this. No? Commas, maybe? There we go. So I'll make lots of new lines here so that we can see what's going on. So now I have to write all this stuff. I do recommend doing this, especially since you don't actually have to write all the stuff when it keeps repeating, because we use the section mechanism, which I'm going to explain next. Okay, so this would be the definition of composition of functions G and F. So how would we do this with, so let me comment this. How would we now do this with section? Let's also have, so that we have something to work with, let's also have a proof that it's associative. Okay, theorem, compose is associative. Now I have to say, suppose I have all this stuff. Yes, A, B, C, more stuff. W, T, D. Sorry. Then I need 3 things. H from C to D. Now I can write down what I want. I want to write down, actually, as it turns out, composition is already defined, but not like, okay. So now let's write down this theorem. So, okay, compose what? I want to compose H and G, but I can't write this. I have to write compose H and G. Okay, so I have to specify the types. So it has to be compose. Is it BCD here? I think. And then compose. So if I compose H and G, that goes from B to D. So now it's going to be ABD. ABD. This is equal to compose. It's unhappy about this bracket here. Compose the other way around. So what's the other way around? The other way around is that I'm going to have an H here. So it's going to go from the inner one is going to be compose. So I want H here. The other one is going to be compose A, B, C, G, F. And then this one goes, help me out, from C to D to E. No, B, C, D. So this one is from A to C. So it has to go from A to C to D. There's an F. Where's the F missing? Here, something F. No. Afterwards, F. Whew. Okay, bye. Can you tell that you're not going to do this all the time whenever you compose 2 functions or 3 functions? Yes?
Could you just tell that the sets are implicit?
Yes, we're going to discuss implicit arguments. I'm motivating explicit arguments, but it's really, really painful not to have implicit arguments. By the way, Lean is smart, and whenever the answer is forced, it will calculate it if you put underscore. So for instance, if I put underscore here, it will be able to tell that that has to be D, because that's the only correct answer. I wonder how many I can delete before it starts to, let's put sorry here. This is kind of suspicious, isn't it? Hey, I could delete everything. Yes. So I'll leave them in for now, but just notice how Lean could tell what they were, even though I didn't specify them. Okay, how do you prove this thing? You use function extensionality. Yes? Function extensionality says that 2 functions are equal if they give the same values. So look at the difference between what happened here. Look at the context. I have A, B, C, D, E, H, I, G, F. And when I do X, a new thing appears with a funny name, XT, because I didn't tell it what the name should be. Can I tell it what the name should be? Yes, I can tell it what the name should be. If I don't, then it just makes stuff up, okay? X. Making stuff up is kind of nasty because now I don't have a good way of actually referring to this thing. I'm not going to type that. And the next time around, it might come up with some other stuff. So yeah, it's very fragile. It's better to give it a name. Okay, now what? Well, I could simplify this. No, I could simplify it and say simplify using compose. Oh, no goals. I could say unfold compose, and then I see what I got, which is both sides are the same. So at this point I can do refold because I played the numbers game. In fact, you never have to unfold like that. You can just say refold because it'll look through the definitions. Okay? Now, we would like to have a sane way of defining this stuff here. So the first thing that we can do is we can have a section mechanism. So for the section mechanism, you would do it like this. You introduce a section. And now the stuff that keeps repeating, which is this universe levels and the A and the B and the C and so on, you can introduce them in a by saying that you have a variable. I can say, I have a variable. Actually, first I have universe levels, UVWT, because I will need 4, right? Then I have variables. And I can just copy this here. I have these people here. Okay. So now, let me call this compose 1. No, let me not call this compose 1. I'm trying to avoid having many versions all called compose. Later on, we'll use namespaces. That would solve the problem. But right now, okay, I'll just say, let's call this one compose 1. It's always good to know how to use your editor, even if it's VI. Oops. Can VI do this? How do I get? But this is compose 1. Okay. Check compose 1. Now we're going to make compose 2. So what happens is this. In a section, you can introduce a variable, and the effect of this is that inside this section, this variable will be known by this. This variable is now known inside the section. So you can just refer to it. You don't have to explain that you have it over and over again. So now, when I type my compose 2, I can just say, I have G from B to C, and I have F from A to B, and this is function xg fx. Yes? Let's also do the associativity. So now I'm lazy. I'm going to copy this because I still have to type the whole thing. So we haven't solved all the problems here. Which one? D. Yes, so now we don't have D. So let's first of all, let's see. See, it's complaining about D. Okay, so I'm going to give myself a D, which is in type T. There we go. You can have more of them. It doesn't have to be one. You could do them in pieces. I could do this. Okay. I could also introduce this D down here again. Okay, it doesn't matter where you introduce it. So, okay. So I have to change all of these to number 2 so that they actually are. And by the way, now I think I can just do refold. Yep, I can just do refold, by the way. You don't have to do this ext business. It's smart enough. Okay. There will always be infinitely many ways to prove a theorem. And then it depends on their style and how you do things, to what you're going to write. This prevalent style in MATLib is they try to make proofs short whenever they can. So like they go for short proofs. So for instance, they would prove auxiliary lemmas with short proofs and then use the lemmas to make a short proof of the main theorem. rather than embed the proofs of lemmas inside the theorem. So this is slightly better, yes?
Does Lean have function extensionality baked in?
Function extensionality is one of the axioms, I think. Yeah. We can discover this by inspecting. You go here and you inspect. So let me show you. You say print compose. No, not this one. Print associativity. So print compose assoc, and you stare at the proof, which is here, and it says funnext, and then you hold your cursor on funnext, and it tells you that this is called funnext something something, and so you can press F12 and it'll go there. No, it won't go there. I missed. I could do check funnext. Check funnext. Funnext is something that says if u and v are universe levels and alpha is in u and beta is in blah blah, is a dependent function from A to sort V, then if, look at this, if for all x, f of x equals g of x, then f equals g. So it's precisely function extensionality, and if you want to see where it is defined, you can press F12. And it's a theorem, okay? It's a theorem. So now, what did they smuggle in? You can explore this further, but it's going to be something about quotients. Okay, can tell me next time what is it that they smuggled in that is non-constructive, because in pure type theory you can't do this. Yeah. Okay. So this is kind of acceptable. It's still not good, but before we proceed, let me show you one important bit. Suppose I'm inside the section and I say, what is compose to? Okay, and it tells me compose to, so let's be careful. Okay, it lists the universe levels, and then it tells me that it depends, you see, it depends on those variables that were actually used. Okay, it does not depend on D, even though I introduced it. It knows that D wasn't used. So this is what you would expect. You would not expect this compose now to depend on all the variables that you introduce, even the ones that are not used in the theorem itself. Okay? So that's a section mechanism, and it's quite useful for this kind of introduce a variable for a little while and then do something like that, and just to organize this stuff. Okay, so the next thing we want to understand is, well, the lecture plan says namespaces and then implicit arguments, but I think this is a good moment to do the implicit arguments given what we have ahead of us here. Okay, so you will agree that this is super annoying that I have to write these ABDs, and we already noticed that I can replace them with underscores, so Lean doesn't actually need them. So let's explain what this is. And I will first explain it on the example of the identity function, which probably is already defined. Yes, it's already defined, so we might as well have a look at it. Okay. This is an annotation which tells Lean how to treat this definition, and we're going to skip this for a moment. Then look at the definition. It says we are going to define id, and there is a type alpha of sort u. We can only hope that there is a sort u somewhere. Oh, here it is. Are we in a section? We're not in a section. Even if you're not in a section, you can introduce a variable or a universe level, okay? But it's good when you introduce a variable. I think it's better to be inside a section, because then the variable disappears, and this way you signal what was your intended use of the variable. It's not just like forever in the entire file, unless of course the file is fairly short. Okay, so if you look at this now, you see that this here is in curly braces. These are curly braces. So when you have an argument, curly braces mean it's an implicit argument. Now, what is an implicit argument? That's an argument that we are not going to provide when we use the function. So when you write id, I can write id5, and it knows that the type is MAT. How does it know that? So this here, what happened was, so maybe I can copy, let me copy the definition and we'll play with it so you will see what happens. So copy the definition. Will it let me redefine it, or will it complain? It complains. Okay, see, it complains. So let's call it id like this. Now it says, I don't know what u is. Okay. Universe u. There we go. So I will first do the usual thing where I don't have implicit arguments. So now, if I want to check id5, it'll say, let's try to understand, it's complaining about 5. Here is a professional advice that professionals use. They read the thing that is written on the screen. You would be amazed how smart you can be if you do that. So here it says, failed to synthesize instance of NAT sort blah. Well, I don't know. Maybe you have to be really smart to understand this one. But what it's saying is, it's saying, I don't know, something's wrong. And what is wrong is the following. We told it that the first argument of id is supposed to be a sort. So it's supposed to be something like a type. But we wrote 5. And there is magic involved with 5, namely that when it sees 5, it does not necessarily assume that it's a natural number. It says there may be many ways to interpret 5. Through something called a type class mechanism, which we haven't learned about yet. So now it's telling me, I don't know how to convert 5 to a type. OFNAT is a mechanism that converts numerals to things, and now it's saying, I don't know how to convert it to a sort. Okay? Because it wants a sort here. So I actually have to type nat and then 5. And now it's happy. Or I could say here something like real. No, I haven't included near. Let's stay with nat. Okay. Anyhow, I have to provide this type here. This is annoying because the type can be deduced from here. Let me do a slightly saner example. Variable a sort u. And let's say we have an element little a in a. So now I say, oh, I have an a here, so let me have an x here. Okay. Suppose I have a sort a and an element x in a. Oh, I'm so used to doing this that, excuse me, there. So if I check, when I check id of x, it says, no, you have to give me the type. Now it's happy and says, okay, yep, id of a of x is in type a. Now it's happy with this. This is annoying because I have to provide a. And moreover, there is another problem. I could provide the wrong a. I could provide, if I had two sorts, a and b, I might make a mistake here. And now it's complaining, and it's complaining about the fact that x doesn't have type a. That doesn't have type b, as claimed. So this is actually error prone. It would be better not to write anything and let the machine do it. So sometimes if you provide too much information to the machine is forced to check that everything fits. It's better not to give the information because then it doesn't have to check. It'll just do the right thing. That's what implicit arguments are for. Implicit arguments means we leave them out. Okay? So that when I use it, now I don't have to provide the type, and it'll know. But how will it know what the type is? Well, if you look at this definition, can you tell what the type is, what alpha is supposed to be from somewhere else than here? Sure. You can tell it from the type of A, you see? So somebody is going to provide this little a, and you will look at its type, and then you'll say, well, that's what the type was supposed to be. This is essentially what Lean is doing. So as a rule of thumb, you don't provide types explicitly if they are already present as types of arguments, because they will just be used. That is a good first rule of thumb on when to make arguments implicit. So the first one is make types implicit if they already appear somewhere else. Okay. So now we can write identity like this, which is kind of cool. Okay. Now, there are a million other ways of writing this. So let's see what they might be. So I could write it like this. Instead of providing the arguments, say, given these arguments, this is the result, I could just write down the type of the function. The type of the function id is for every source alpha, alpha arrow alpha, and now I have to define it. Oops. Now I have to define it, so it's a function, okay, which takes what? Let's see, x to x. Will that work? That seems to work. No, it doesn't work. It works, okay? So what happened here? I could also do this, I suspect. Yeah, but now it's saying you're not using that. Okay, let me use that. There we go. So let's think about this one. So here I said, this is going to be my type. For every alpha in sort U, I will give you a function from alpha to alpha. So that's a function, actually, an element of a for all. For all is just pi. Pi, the elements of pi are functions. So it's a function. It'll take an alpha, and then it'll take an x, and then it'll give you an x. So this is now quite similar to what we had here. Maybe to make it exactly the same, I'd put a here. It's the same way. Notice how I used curly braces in the function because I also used curly braces here. So curly braces always indicate an implicit argument wherever they stand. Like in a for all, for instance, they could be in a for all. As you noticed, I didn't have to write the alpha in the function because it's implicit. I could say here, just leave it out. But then I have to leave it out all the way. And then the machine is just smart enough. Okay? Sometimes you do want to specify the function. So suppose I want the identity function on natural numbers. How do I write the identity function on natural numbers? If I write just id, then I get the generic id. If I write id nat, did I get what I wanted? What is id nat? Ooh, it's unhappy. It doesn't know how to define. Okay. Oh. Yeah, it doesn't want to calculate this. Id nat is nat. It's the identity function applied to the type nat, which is nat. So this is not the correct thing. What I really want, because what happened here? When I said id nat, it said, okay, it's id, and this a here is nat. So alpha is something like a universe, wherever nat lives. So what I really want is I want to set the first argument. So you can turn off implicit arguments by putting alpha in front of your function. So if I say alpha id, now I turn them off. So now I have to provide them all again. So now this won't work because it says, no, you have to give them all. So now it works. So if I do this, I get a function from nat to nat. Which function? The identity function from nat to nat. Okay. There is something called strict implicit arguments, where this has double braces, like this, okay? Which are fairly exotic, and you will not see them much, so I will not explain them now. Well, I can explain them quickly, but I will not explain how to use them. Okay, so here's a question. Suppose you have something like you work with lattices, okay? And every lattice has a bottom element. So you're going to have something called bottom. Let me do this. I'm not actually going to define anything. I'm just going to sort of make an outline of what I would want. So presumably, we might have a space, we might have some sort of type of all lattices. Okay, and every lattice, so let's say these are bounded lattices, so they have bottom elements. So now, presumably, we're going to have something that's called like bottom. Yes, how would bottom work? Well, it would go from every lattice, so it would take a lattice L and it would give you an element in L. Yes, for any lattice, it'll give me what? Oh, sorry, like this. I need to do more. So every lattice would presumably, we will see that, I mean, this is not the way to define things, but I'm just introducing concepts here, so bear with me. So for every lattice, we have its carrier, which is a type. The carrier of a lattice. And so here, for every lattice L, I have an element in the carrier called bottom. Okay? The way I wrote this, now, if I have some specific lattice, say some lattice M, suppose it is a lattice, I can say, hey, what is bottom of M? And it's going to tell me it's something in carrier of M. But if you work with lattices a lot, you are going to get tired of writing bottom M, bottom L, bottom, like always explaining which bottom. You will want to write this. Okay? And you will hope that it's clear from the context which bottom is meant. So what would be the thing to do? Well, you could make this one implicit here. Yeah? But now bottom is something super weird. It says bottom is in the carrier of question mark M447. What happened? What happened is the following. When I typed bottom, it said, ooh, bottom has an implicit argument L. Let's introduce a new unknown value that is called a meta variable. Okay, let's introduce a meta variable, so something we don't know what it's supposed to be, and stick it in. And so it introduced question mark M447. And it's hoping that at some point it'll find out what that is supposed to be from the usage, from the context. Somewhere the information will appear, but not yet. What strict implicits do is, what I might want is, I might want to say, no, please don't do this. So I want this still to be implicit, but please don't do this. And then I put this in. So now bottom is still a function. Okay. So you can control, this is controlled when the last argument is implicit, whether it should be stuck in or not. Yes. So let's make this point again. If I have a function, suppose I have a function f, and suppose that its arguments are going to be implicit. Do I still have a? Oh, I still have a. How cool. And then the next one is not implicit, and then the next one is not implicit. So if it's like this, then when I apply here, when I apply something in B, suppose I have something in B, when I say f of B, doesn't know about C, so let's make this one in B. Okay, no. Am I going crazy here? It is complaining that something is wrong with my universe levels. So how about if I'm just explicit? There's a universe level U. There is A, which is in type U. And they are just all from A, and leave me alone. Okay? Now what? It's already been declared. Okay, cow. Now what? happier here. What did I do? Section, universe U, variable, but I have U and B. Why does it not allow me to use A?
You start the new section in the section.
Yeah, does that matter? I'm now outside of the, I'm outside of the section, so this section should be lattice example. Okay, let's debug this. Invalid occurrence of universe level U1 at F. It does not occur at declaration, nor is it explicit, blah, blah, blah. Blah, 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 blah. What is the universe level? Oh, we should say what the result is. Here. So let's say it's this. Okay, now we have an F. Thank you. Now I can do B. And if I do B, then this has to be B. So now, suppose I have an element in B. I can say, if I apply F to B, by the way, you see how this is yellow? It says you're not using X. It wants me to write underscore here to be nice. Okay, so check F of B. This is crazy. Application type mismatch. F of B, argument B has type B, but is expected to be a sort. Really? Check F. F wants two sorts which are explicit. Ah, up here, I said that A and B are arguments, but because I put them in ordinary parentheses, they're explicit. I can also make these guys implicit. When you introduce a variable, you can make it implicit. So everywhere it's used, it's going to be an implicit argument. Now, F has implicit arguments. I can actually type F of B. Now, when this happens, it can tell that there is a missing argument A. When you see F applied to B, it says, okay, so it must be the case that this little B here, it has to come from here. And there is a missing argument from A up front. So it will insert it. It will automatically insert one for A. It can tell, you know you can do that. But suppose we have a third one.
As a meta variable?
Yeah, this is a good question because I'm not using it. What the hell did it do?
Inserted it as a meta variable and then started it. Because it-
That is very, very dangerous. Because what if A is empty? I guess it's okay because we're not using it. Yes. So, yep. This will be, let's make a less confusing example. No, we don't have products. Okay, we'll stay with this one. My point is this. What happens if there is another implicit argument at the end? Now, when you see F of B, there are two ways of reading this. You could read this F with secret X inserted, then Y set to B, and then a secret Z is inserted. Or you could not insert the Z. But only with the last one you have this freedom. X, you must insert, otherwise B doesn't make any sense. But Z, you don't have to insert. You could just stop there. You would get a function which expects an implicit argument. Should you or shouldn't you? That's the difference between this kind of brackets and this kind of brackets, the double braces. So you can either type them as double braces or / double braces, and then there's some fancy unreadable braces. So I'll stick with this, it's more readable. So if you do this, then it will not automatically insert the last one. It's a minor detail that I spend way too much time explaining now. Okay, so we have the section mechanism. We have the variables inside the section mechanism. We have implicit arguments, which are curly braces. As a rule, you make an argument implicit if it's a type that can be seen somewhere else in the definition. That's like your first rule. That'll cover 80% of the examples that you need to know about. You can make variables implicit when you declare them, and then they will act as implicit arguments. You can declare arguments implicit also in for all statements, and they will be implicit. It doesn't have to be as explicit arguments to a function. The last bit, which I'm going to explain now a little bit, and then we'll go to a break, is namespaces. Okay, so this touches on a more general organizational feature, an organizational problem that one faces whenever you have to deal with large amounts of source code. It can be just ordinary code, it can be formalized mathematics code, but it's always the same problem, which is I'm going to define 20,000 things. How am I going to organize the names of these things? Because if it's 20,000 of them, it's going to be difficult to remember, and I need some sort of an organization type thing. For instance, I don't expect them to all be in one file, hopefully. Very long file with 20,000 definitions, that's not going to be workable. So we need ways of structuring names of things, just the names, and also ways of structuring code so that, for instance, code can be divided into separate files and modules, units of software. Yes? Units of software or units of formalized code, that is dealt with in various ways in various programming languages. For instance, in Java, you have packages and classes, and they provide a hierarchy of code. In something like Python, you have modules, right, which are in files, and then you have classes, and then you have things inside classes. So that's also organizing things. In ML style languages, you have a thing called modules, where a module is just a unit of code that contains some definitions. So orthogonal to this feature is naming conventions. Even though many programming languages combine naming conventions and code organization. For instance, in Java, if you want to refer to a thing that is in package cow, you write cow dot something dot something. You actually say where the thing is found by saying, package name dot class name dot something inside a class. And this is quite common, and it happens in many programming languages. You access something in some other unit of code by providing a path to it, which has these dots and units. And that is it. That's not how mathematics works. Mathematics does not do that. Because if it did, you would do all of number theory in one course. And afterwards, you would never do any number theory ever again. You could do something else called number theory prime and do more number theory prime there. But then whenever you refer to a theorem in number theory, you would have to say it's a theorem from number theory prime. It's not a theorem from number theory. This, of course, is not going to be good, because sometimes to prove a theorem in number theory, you have to use, say, complex analysis. But how do you formalize complex analysis? Well, by formalizing first real analysis. But how do you formalize real analysis? You first construct real numbers. But to construct real numbers, you need rationals, integers, and natural numbers, and you have a circle. So it will not do if you want to have all your theorems in a single unit, all your theorems about natural numbers in a single unit called natural numbers, then you're going to have a problem, because you would have to prove all theorems about natural numbers before you construct complex numbers, because they depend on natural numbers. But then you could never use complex numbers to prove theorems about natural numbers. So this is not the correct way to organize mathematics. Mathematics is much more entangled. So on top of the module hierarchy that Lean has, files, it uses files to organize to organize units of formalized code. On top of that, they have something called namespaces. C++ also has namespaces. But the namespaces in Lean were invented by hippies. They're completely free. You can do arbitrary junk with them. So to organize yourself in any way you seem fit. What are namespaces? These are, when I define a thing, I can just say, let me show you. I can organize a namespace. I start a namespace, and it's a lot like a section. Now I can introduce variables and all of that. But most importantly, when I define something here, and in here I have a cow. You see, cow is a natural number. Once I get outside, it's not called cow anymore. It's called foo.cow. Now, you see? So whatever you do inside the namespace, once you get out of it, is going to be called namespace dot something. I can have even subspaces, sub namespaces. Can you guess where dog can be found? If I check it here, so here it's called dog. Here it's called bar.dog. And here it's called foo.bar.dog. Yep. Now, the neat thing is, suppose this is our number theory. Later on, I can start the same namespace again. It could be in a different file, totally unrelated. I start the same namespace and I do some more. So now I also have a rabbit in the same namespace. So when you do number theory, you can have a namespace called number theory, and whenever you want to do a little bit of number theory, you just do it. You don't have to open a namespace. You can actually do it like this. You can just literally put something in a namespace. When you define something, you say it goes into that namespace. The namespace does not have to exist. You can just create it. It's totally happy. So as far as it's concerned, namespaces are just these dots, strings separated with dots. The user wants one, sure, they can have one. I can tell you that this is not entirely ideal because I spend a lot of time debugging a library on graphs because I use the namespace with a capital letter, but it was really with a lowercase letter, and then I spent a long time figuring out what was wrong, and I kept making this mistake. You put something in one namespace, say graph with a lowercase g, and then you try to use it and you write graph with the uppercase G, and then you're like, oh, it doesn't know about this. I forgot to import. No, I did import. Oh, what is going on? So yeah, namespaces. One other thing. Often, and you will see this in practice, the thing, Lean, can figure out which namespace something is supposed to come from, and then you don't have to write it, and you just write like this, poodle. Right now it doesn't. It has no idea where poodle comes from. But in certain circumstances, it will know. Namely, whenever there's an argument that already has a type that will tell it where namespace to go to. So whenever you see just dot something, that is a convenient way of not specifying the namespace. I should also tell you that these namespaces work beautifully because, for instance, things involving natural numbers are in the namespace called NAT, just like the type. The type NAT itself acts as a namespace. NAT is a type. See, it's a type, but it also acts as a namespace So now I have all sorts of things in there, everything related to NAT. Okay? So implicit arguments, strict implicit arguments, sections, namespaces. So that's the theory for today. Let's have a break and come back in about 15 minutes.
That allows you, if you have to prove some statement that they're like super symmetric,
Yes.
then you just have to swap the variables. There exists a technique that allows you to.
So you would like a tactic in Lean that where you prove one case and then you say the other one by symmetry? I know that there are some people working on this. Mattia Prittner, of all the people, with Ohat Hamkamar, and I think they're doing this because they're into PL. I think they're doing this in the context of programming languages. The idea being they're not the only ones. I'm sure people have thought about such tactics, but I know that they specifically do it. And the idea would be that, for instance, when you have balanced trees, you know, when you program balanced trees, you always have the left case, the right case, and they're symmetric. The idea is that you could explain this to the programming language and you just do one case and then you say the other ones by the following symmetry. So the idea, of course, is present and old, and I don't know if Lean has it. There is a file that has all the Lean tactics, which we can look at, but it's going to be a lot. So I think it might be this one. No, it's not. It's a bit difficult to find. It's somewhere. I give up now. So, but if you search, it's generated. It's something that is generated by Lean and dumped into a markdown file. And then with the documentation, you can browse through that. That would be, I guess, the safest way, because there are a lot of tactics in Mathlib. The other one is, so something to just think about next time, but I would imagine such a tactic to be quite difficult to implement. If you think about it, how you're going to do it. It's not, you know, it might work in simple examples, it might maybe worth having, but I'm just saying, okay. And I know that there has been prior work on this particular topic, so it's more like a literature search is warranted to answer your question. Okay, let's just do some exercises, unless there are some questions. Here I did not explain the difference between type and sort, and I'll come back to you after next time. Okay, so now we can close this, and we're going to open mathematics in Lean. And we're just going to do the things you were supposed to do anyway. Okay, and I want to comment on the kinds of things that one needs to do. Actually, no, let me go back, before I do this, let me go back to do one more thing here, to show different styles of suppose we have some propositions. Let's do this one first. Suppose we have some propositions P, Q, R, so some truth, okay? And we want to prove the following, something like this, that P and R, P or R and Q or R implies P and Q or R. Okay? In how many ways can we prove this? Okay, so let's see. So the first one would be by tactic. So you go into the tactic mode, and oops, it says, hey, you need to prove this. Okay, it's an implication, so you do an intro. Okay, now tutorials that you're going to read online, a lot of them will say use intro. Never use intro. Intro is dumb. You want to use our intro. Our intro is smart because it allows you to take things apart. So for instance, if I just say our intro H, now I have this, but it's actually really, it's two hypotheses. I don't want a single hypothesis here. I want the first hypothesis to be P or R and the second one to be Q or R. I want to take them apart. And I want to take them apart once I see. So first of all, I will use our intro. I see that I need to do an intro because it's an implication. So then I say, I want our intro, I say H, and I say, oh, no, I actually wanted two things. Okay, so if you wanted two things, then in our intro, you just put in these braces, and you say, I want H1 and I want H2, like this. And it'll take the assumption and it will decompose it into two parts, which are H1 and H2. And now I can work with this. Okay, what should I do? Well, I kind of want to split cases on whether P or, like, I could split cases on H1. Yes, say if P holds, I'll do one thing, and if R holds, I'll do another thing. So you can do that. You can say cases H1, and notice how here it introduces two cases: intro in left, intro in right. See, now I have two cases to prove, and I'm working on this one, the first one. So now I say, okay, I got two cases, \dot, I go and I work on the first case. So now it's showing me the first case. So these bullets are the separate items. I say, okay, what do I know? What happened? I know that P holds. Yeah, I know I'm in the first case and P holds. So first of all, it's kind of annoying that I have P holds, but I can't name this thing. But okay, let's try to survive. What would you do now?
Can I find cases H1K or something to name?
You want to name it?
I think without width.
Just see. Okay. We will get there. Let me show you the one where I don't name anything and I use bullets. Okay. So now I say, okay, I have P, but I want to prove P and Q are R. And it's kind of confusing because there are no parentheses there. So I go here and I say, I remind myself, oh, or, okay, yes. Okay. So which one am I going to prove? Does that depend on H2? Yes, I do cases H2. So now I have, okay, so I'm now considering cases H1, and inside of that cases H2, and it says, okay, I have P and Q. Once I have P and Q, I know that I want to prove the left disjunct. So I say left, and now it says, okay, how are you going to prove P and Q? Use the constructor. So constructor, there is one way to prove P and Q. When there is one way to do something, you can say constructor, it'll say, okay, we will use the one way. So this is the introduction rule for conjunction that it used. And so now I say, okay, I'm here. I need to prove P, and I have assumptions P and Q. But I can't name my assumption because I didn't name it. It's called HT1 thing. I'm not going to type that. There's a tactic that says, you figure it out. It's one of the assumptions. And here, it's one of the assumptions. Okay? So now I am done with this case. So I now go to the next one. So now I have P and R. I'm looking here. Here I'm looking, always at the top. I have P and R, and I need to prove P and Q or R. So I could now do R. So I go to the right. I say I'm going to prove the right disjunct, and it's an assumption. Yep. And this is one way of working. Okay, I'm not done. I have to go back, and there's one more case here. I have Q or R and R, and I have to prove P and Q or R, so that I know. I have the assumption R, I can prove this R, so the right one, it's an assumption. Congratulations. That's going to be a lot of writing, especially when this kind of argument is part of something fancier. So let's see what we can do with this stuff. The tactic language allows a lot of flexibility. So I'm going to start the same way again and just show you.
This work with just
Yes, this would, okay, so this would work with just Tata, which is a tactic. But I think you would have to do import. I think you have to import mathlib tactic. I think so. Let's see. So that's going to be our second one, which is Tata. Does this work? Maybe I imported too much. Tata is evil. Yeah, it worked. Let me see if it works without the import. I'm afraid I'm going to have to wait again. Yeah, see, it wants. I probably imported too much. There is less than I can import, and I can try to discover that, but okay. So, Tata will do tautologies, propositional tautologies, and it's super happy to use excluded middle as soon as it can. There's another one. Is it called? I think Mario wrote another one. I don't know where it's hiding, which is intuitionistic, which will not use excluded middle unless, then you use. Okay, so let's go back to how we would do this with our bare hands. Okay, so first, now what? Oh, dister 2, this is dister 3. Okay, so we're again here, and we say we want to consider two cases, and so we say cases H1, okay? But now sometimes you want to do these cases out of order, or you want to be a little bit more specific, because here, when you see this bullet, you don't actually know, it's hard to tell which case is going to be. So you can do cases, and then you say which case you want to consider. So let's consider the second case first. And it says here it's called intro in R. Okay, case intro in R. And now I'm in the second case, like this. So instead of the bullet, I write which case I want it to be. So now I can say, oh, it's right. And by the way, I don't have to do, I can go new line assumption, and now the case is over. But this new line business, sometimes you want to be a little shorter, you can do it like this. That means do this, then do that. Yes. Also, I get the ability to name things. You see here, it's not named. Okay, so let's name it. Now it's called G. Okay, so I could do the other one. It's called case intro in left G. And now I'm doing them out of order, but now I have to still consider the cases for H2. And now I have two. One is in left, and this one is constructor. Okay, so let's do this one again. Okay, so let's learn a little bit every time. So constructor, what is the problem? Constructor. Okay, so it says you have to prove P and okay, here, where were we? Here. Sorry, I have to go left first. I say go left, and then, oh, if I just say constructor, it just picked the first constructor it saw. Don't do that. It was straight. Okay, so it used the left. Okay, so P and Q, constructor, you see I have two cases. P is the first case. I could now say case H left. I'm not going to write case. Okay, it's too much. But the point is that both of them are assumption. If you go up here, both of them are assumption. So it seems kind of silly. I can do this. I can say, this means perform this tactic. You are going to get some number of sub-goals. On each one of them, do this thing here. Assumption. This is not the same as a single, because you see, if I do a single one, what happened was it generated two goals, P and Q, and then only on the first one it used assumption. Only on the first one it used assumption, and I'm still left with Q. So this just means the next thing you do after this is assumption. This means on every sub goal that you generated, perform this tactic assumption. So we could now also write it like this, for instance. Yes?
Does it have to solve all the sub goals, or
Does it have to solve all sub goals? I don't think so, but I'm not sure. This is a good question. Will it complain if it doesn't succeed? Actually, we could say, let's do us. I'm afraid simp. Oh, okay. Simp will not. It made no progress. What's a tactic that is going to that doesn't do anything? It's it tac in it's it tac in cock. I don't know what it is here. My God. Okay. Homework. Does it want all of them? Okay, so we're not done yet. There is one more case, which is, now we know what to do. It's write assumption. Okay. So this was what changed. Instead of bullets, I have the cases. Now, I recommend bullets if they don't spread across 3 pages. If they're kind of short, it's okay. But if you have very long proofs and you have these bullets, you come, after 1 page, you come to the next bullet, you can't tell like which bullet is this. So in that case, it's slightly more informative to have these case. You name them, because then it says, okay, this was the case from. It's a little bit easier. Also, maybe a little bit more robust to name the cases. Okay, that's not the end. Yes?
It seems like it doesn't have syntax highlighting for this style of.
Here? Yeah, I don't know why it does not highlighting case. Good question.
But also not very.
What's this incorrect?
Nothing. Just add intro now. Also isn't being.
But it was before. Maybe I'm not done here. Maybe I'm just faking it. Nope. I don't know. It'll maybe come to its senses. Who knows? We shall see. Okay. Okay, so this is a common pattern that I do cases on H1. Like I introduce H1. You see, I used our intro to split my assumptions into 2 assumptions, but now I want to do cases on one of them. So I do cases H1. But I can actually tell our intro to do it. I go here and I say, hey, split this into 2 cases. Call them both. Let's call them H1 and H1 prime, just for fun. So now already our intro is introducing the cases, you see? I have them both. Yeah. So the cases immediately happened. Our intro did it. And now I go la 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 like before. Or I could actually split this one as well. And then I will get 4 cases. I just get all of them. So our intro, if you use brackets like that, then it will split into parts, whatever you have. If you use a bar, it'll say that's going to be a case split. And now I go like whatever, left constructor assumption, right assumption, right assumption. No, I should actually read what's on the screen. Which one is this? I have R. Yes, okay. Right assumption. Now I have more cases. One of these cases is kind of silly. Right assumption. Oh, that's another way that you use our intro. We are not done. Okay, we could actually, this cases business, we could actually write it by writing case statements. So let's try to do that. Let's not use tactics at all. Just write down the proof term. If you came from Agda, you will think this is the normal way to do it. But Agda has very good mechanisms for that. You will see here they're maybe slightly less good. Okay, so now I'm going to start, because I want to do cases, I will start naming these arguments here. So I will say, I don't want it like this, I want it like this. I have H1, which is P or R. I have H2, which is Q or R. And I want to prove this thing here. But now, no by. Not allowed to do by. What do I want? If you put down underscore, you find out what needs to be done. You need to construct this. Okay. What did we say we wanted? We wanted to do a case on H1. So let's do case H1 with match H1 with, and it says unexpected token and expected blah blah blah. Okay. So now I have to say what the cases are. One of the cases, okay, now I have to know a little bit about OR. So because I'm splitting an OR, I should go and look at what OR is. I'm pressing F12 to get myself to the definition of OR. OR is an inductive. So when you see inductive, this is going to be a whole lecture, what inductives are. But in general, it means an inductive type means that we're going to have several generators, and the type is generated by these things. So we have two generators called in left and in right. In left is something that from A gives you an element of OR AB, and in right is something that from an element of B gives you an element of OR AB. So the two cases are called in left and in right. So they should be OR in left and then something. See, G is the P, or they are OR in right something. Now I can do the next one. So now is a good time to observe that I can delete the namespace. And this is common. How does it know that this needs to come from OR? Because that's the only thing that's going to make sense, because H1 has type OR, and because we're matching H1, it already knows we're matching at an OR, so I don't have to keep explaining that this is going to be an OR. So this would be more idiomatic. Delete this. Now we need to produce a proof of P and Q. Well, it's always P and Q and OR, but which one is this? Oh, we have to do a case on H2. Can I do two cases at the same time? I could now do another one. I would start here, match H2 with, okay, let me do this one. In left, AG, I don't know if, okay, sure. In right, like this, okay. I have P and I have Q, and I want to prove this, so I need to go to the right, to the left, so it's an in left, and now it wants a P and Q, so then it's an and intro, so I don't have to say and intro, it will know that it's an and, presumably, of P and Q, G and K. There you go. What happened? And intro. Let's look at the definition of and. And is a structure that has one field. No, it has one constructor called intro, and it will want two things called left and right. So to construct something in this structure, I say intro, and then I provide two arguments, one of type A and one of type B. So here, this is precisely what I'm doing. I'm supposed to construct P and Q, so I'm constructing both. I don't have to write this because it will figure out where this is supposed to come from, because it knows that it wants an end. Okay, here, this is the case where I have an R, so there's going to be an in right of K, and this is going to be an in right of K. So now we didn't use any tactic. G. Thank you. Let's compare the proofs. So print distr 4. Let's do 1 first. Distr 1. Would anybody consider reading this? Fun PQ. Okay, so we get proof of P. No, we get a proposition P, we get a proposition Q, we get a proposition R. Okay, then A is a proof of this thing, and now our assumption, server process file crashed. Okay, excellent. What I would like to compare is what these different proofs look like. And so see, it has AND cases on, OR cases on, motive, something, 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 okay? Then let's look at the one from distr 2, still AND case are on, okay, thank you. Two is the one with Toto. Yes, so if you look at what Toto found, actually it wasn't that bad. Toto kind of found what we wrote by hand, I think. This is Toto. Ah, decidable, you see? The damn thing, it's like using proof by contradiction. Okay. Right, of course you're gonna crash. You're using proof by contradiction. It's your fault. Okay. Let's look at distr 3. Well, I suppose I'm just gonna keep crashing it. I do want to look at them. Okay. Distr 3 still has AND cases on, OR cases on. What is this AND cases on business? AND cases on. Nope, I failed. Check AND cases on. Okay. AND cases on, where is this defined? Actually, it took me here. So because it's some automatic magic that happened. When you define a structure, it gives you this ability. Okay. And so it's using that. Let's see if we can read this. AND cases on. Okay, there's a universe level, there is an A and B, which are propositions. There is some strange thing called motive, which is from A and B, we're trying to prove something. Oh, it is what it is that we're trying to prove from A and B. Then we have T, which is a proof of A and B. And then we have something that will introduce the motive, and then, okay, sure. It's induction. It's the induction principle, yes. But this one still used cases on, because here I used cases. Now in distr 4, let's see what our intro does, because our intro actually maybe also used cases for. Let's see. Is this different? Maybe are all the same. Yeah, it's getting more compact, you see. Our intro is more compact. And then the fifth one. The fifth one uses match directly instead of cases on. Cases on is like match, except it's like a function that you apply. Match is a syntactic construction.
Are these normalized?
No. No, they're just like exactly what they are. Okay, so these are the different styles. The idiomatic lean style is this one. You really want your proof to be short, and especially for a proposition, not for a construction, but for a statement, you don't much care how you got there. Okay, so you're just gonna say total. You would not normally want to spend your time proving things like this. Okay, you want to use heavy weapons all the time, just make things go away, because you're interested in proving things like, you know, counter Bernstein. That's in the mathematics in Lean. The sets function has the counter Schroeder-Bernstein theorem, that if you have injections in both directions, then you get a bijection. So I recommend going through that proof. That's like a real proof in Lean in your the material. It also secretly uses excluded middle, so extra points if you can tell me where it used excluded middle. It must, by the way. Okay, so I think we can be done here. I just wanted to show that there is a lot of scope when you make proofs. It depends a little bit on your personal style, but if you're going to contribute to a large library, such as MATLib, then before you do, you should poke around and see if there's some way to, if they recommend a style. Code style guideline, documentation style guideline. Code style guideline is going to say variable conventions. Okay, you should use lower Greek letters for generic types. You should use ABC for propositions. So this one I kind of observed. This one today I mostly broke. This one I broke because I called them PQR. This one halfway because I had ABC also. I used uppercase, so I broke this one because I said H1 and H2 is uppercase. Okay, so still broken, and we didn't have any lists. Line length should be 100. Okay, sure. You know what's going to happen many years from now? There will be a research paper in digital archaeology where somebody is going to have a graph of line length in source code throughout ages, and they will based on that, they will deduce how large monitors were, because all monitors will be gone because of the apocalypse, but somehow the digital stuff will survive. So observe the line length unless you want to be classified in the wrong century later on. And so on. Module doc strings, what they should look like. Oh, by the way, things that are like this. So when you start a comment but you put a bank, that's a doc string. A doc string means this is something that's going to show up when documentation is generated. So read these things. If you've never had the opportunity to contribute or to write source code where you're actually supposed to write documentation and so on, maybe now would be a good time in your project. You put in doc strings and you just generally try to make yourself look like a civilized person and not just some random student typing clean code. And then, lots of other stuff. But, hey, you can read this in half an hour, right? Okay, any questions? We're done for this week. Oh, let's just quickly have a look at what I thought would be a good plan for this week. Okay. Of course, I did not expect people to massively read all of mathematics in Lean. Even kind of going just through the first 4 chapters is a lot of work, let alone the whole thing. So continue going through mathematics in Lean. Don't just read it. There are exercises in there. Get rid of the sorries. It's written well. It'll teach you the right things that you need to know for later on. So please do this. The next thing that you should start thinking about is start thinking about what would be your class project, because I'll let you pick your class projects so that they match your mathematical interests. I will probably be the person who will insist on it not being humongous and over-engineered. So it shouldn't be too big. It should have several goalposts. So it should have, here's the first step, here's the second step, and the first step should be really easy, and the second step should build a little bit more, and the third step should build a little bit more. Because my experience shows that it is very easy to be too optimistic about the amount of formalization that one is going to actually carry out. So let's have these goalposts so that you're not left without anything if you just have a single goalpost at the end. One thing that I recommend to give you an idea also of what you might want to do is you go to the MATLib documentation. MATLib is down here. Now you open this, it gets scary. Oop. Okay. And you poke around the stuff that you are interested in. And I hope nobody is interested in this stuff here. Okay. So things. Wow, halting Oracle languages. Really? I'm interested in this stuff. With partial recursive functions. Ah, interesting. Okay. Poke around. If you find that there's a theorem that you could prove that it's not there in here, that is a possible project, but be warned. If you're going to build on top of MATLib, you will first get to familiar with MATLib more than if you're just a random user of MATLib. You want to contribute to MATLib. So it will take a little bit of time to get acquainted with MATLib, to use it. On the other hand, I would imagine that time is well invested because you will have a lot at your disposal. If you have a project where you don't rely on MATLib so much on what's already in it, then you will be more in control. You will know precisely what is going on and what needs to be formalized. On the other hand, you're not going to have all the knowledge that is already available. So I don't know. So start thinking about it. So there's category theory. You might get the impression that everything's been done and that there's nothing that you could possibly do in your project. Okay? You don't have to avoid MATLib. Your project does not have to be like the thing that you formalize does not necessarily have to be disjoint from MATLib. You could, for instance, try an alternative approach or organize, like give a different proof of a theorem or something like that. It's okay. Yeah? If your project is exactly like a theorem in MATLib, with the proof going the exact same way, I think the temptation to just copy will be too big. That's probably not a smart idea. Okay, now we stop. So keep going, mathematics in Lean, keep going, and start thinking a little bit about what you might want to do for your project. Next week, we don't have any classes, so you should be, it's national holiday. So use the time well to learn more Lean.